So our first speaker is Igor Boettcher. So he got his PhD with Christoph Wetterich in Heidelberg, working in BCS-BC crossovers and ultra-cold Fermi gases. And then after a postdoc at Simon Fraser University in Canada with Igor Boettcher, he came as a postdoc to the JQI in October 2018. He's been working with my group, but also others. And he's actually starting as an assistant professor at the University of Calgary in Alberta, in Canada in just a couple months in February. So he has won many awards and fellowships, including the Otto Haxel Prize in 2011 for an outstanding diploma thesis. He came to the University of Maryland already as an expert in condensed matter and AMO, but has now also embraced the quantum information science. And he's made lots of great contributions across all three of these fields, and he will talk about one of them today.
All right, thank you so much, Alexei. Let me start sharing my screen. Okay, thanks again, and thanks, of course, to the organizers for giving me this outstanding and amazing opportunity to talk here. Full screen mode. So I want to be talking about quantum simulation of hyperbolic space with circuit quantum electrodynamics, and we're going from graphs to geometry. And this is pretty much covered in this nice paper we wrote together in Alexei's group, together with Alicia and Przemek and Ron. And it has recently been published. It's featured in physics, and it has also been selected as an editor's suggestion. So if you want to read a bit more about what I'm sketching today, please feel free to look into that. Let me start with a little advertisement. So as Alexei was pointing out, I will be starting as an assistant professor at University of Alberta in February next year. So if you wonder where that is, so this is in Edmonton, pretty far up north actually. So winter is quite cold, but it's a dry climate, so it's actually not bad. And the summers are beautiful. And so there are actually some postdoc and PhD positions available. So if you're interested in any of the stuff I'm talking about, please feel free to contact me. And if you maybe want to read more, there are two very beautiful news written by our Bailey Bedford about the hyperbolic physics I'm talking about today, but also about some physics of spin-free half topological semi-metals that I won't cover today, but will also be a part of our research group. So let's get right to it. What are four of, say, the biggest open challenges of physics, and especially theoretical physics at the moment? I think these are four good candidates to mention. One of them is quantum gravity, like the physics of black holes, where general relativity and quantum physics meet and need to be combined into one theory which embraces both, which is an open challenge. But also the physics of quantum many-body systems, where the physics of the constituents are usually known, but it's unknown how they interact to make a big collective conglomerate. And as an example, I've taken here the so-called quark-gluon plasma, as it is realized, for instance, in heavy ion collisions, where we probe the physics of quarks and gauge theories at high densities and high temperatures, which is relevant for the early universe, for instance. Another field of active research is quantum information, together with quantum computation, where you, of course, want to utilize the power of quantum physics to gain an advantage in computational tasks, and also understand the structure of quantum physics deeper on an information theoretic level. Now, I want to convey the idea that all of this is intimately connected to hyperbolic geometry. It's not such a surprise for quantum gravity. After all, it deals with curved space, which is non-Euclidean. But even quantum many-body systems are related to hyperbolic geometry through the insight, which is usually called the holographic principle, or goes under the name of ADS-CFT correspondence, that if we equipped our space with an extra dimension here, and say this quark-gluon plasma would be living on the boundary of this space, then many of the properties of this strongly correlated system, this complicated many-body system we have no idea how to describe, many of the properties of this system on the boundary, this quark-gluon plasma, are captured by the physics in this extra dimension of a gravitational theory. And this extra dimension has a hyperbolic geometry. So it's very interesting to study the boundary of hyperbolic geometries, and this is also relevant for these black hole physics. In the context of quantum information, where we want to understand the underlying structure of, say, quantum states, of Hamiltonians, of ground states, a technique emerged which is called MERA, for instance, or tensor networks, if you wish, goes in a similar direction, where you represent quantum states through a connection of certain links. And then you might ask, what is the geometry of these connected bunches of qubits? And it has been pointed out by Brian and others that this might actually be a hyperbolic geometry. And in the context of quantum computation, a question you might wonder is that, okay, you have 50 qubits. That's what you can work with. What would be a good arrangement for these 50 qubits, which is very efficient and maybe good for error correction? And in this context, also hyperbolic lattices and hyperbolic geometries show up because they might have supreme properties for connecting these qubits. So all of these questions are related to hyperbolic geometry, and it's a beautiful topic in itself. And right into this came this nice headline based on this very nice paper by Alicia and collaborators: Strange warping geometry helps to push scientific boundaries. And it's about this paper, Hyperbolic Lattices in Circuit Quantum Electrodynamics. And the second I heard about it, I was immediately enticed by it. And it's a very beautiful work. And I decided to work on this and make some contributions to these wonderful experiments. So let me tell you a little bit about what hyperbolic lattices are. Then I'm going to tell you how we made a little continuum approximation to capture some physics of these experiments. So let's talk about hyperbolic lattices to begin with, and maybe let's recall what lattices you might know. Well, lattices we all know in the plane are, for instance, the square lattice shown here, or the honeycomb lattice, or the triangular lattice. And to bring them a little bit in order, I introduce this so-called Schlafly symbol after the Austrian mathematician Schlafly, which is these curly brackets with two integers p and q. And this p tells you that the lattice is made from regular p-gons, and the q is the coordination number of this lattice. So for instance, at honeycomb lattice, this is made from hexagons, p is 6, and the coordination number is 3. 3 edges meet on each vertex, so this is 6, 3. The square lattice is 4, 4, obviously, and the triangular lattice made out of triangles is 3, 6, because the coordination number is 6. Now you might wonder, okay, is there any more? What about, say, 127 gons? Can I do that, right? Or 128, or where does it stop? From some very basic geometric considerations, you find that actually the condition, if you want to tessellate your whole plane, so think about your bathroom tiles and you want to tile your bathroom, then the tiles can only be p and q, where p minus 2 times q minus 2 is 4. Obviously, these three lattices satisfy this condition, but they are also the only ones. So this is really the finite and complete list of tessellations of the plane with regular p-gons. Now, why is that? You can see it if you were to start tiling your bathroom floor with the wrong tiles, you would already run into problems very quickly. If you take hexagons, they fit nicely, very snug, you can make a big lattice out of this. If you were to use pentagons like here, you see that, well, you have too much space already. So you don't have enough tile to cover your whole space. So you certainly won't have a whole tessellation of your plane. But now you all know, if you take, for instance, a soccer ball, you can very well cover a soccer ball with pentagons. And the reason is that the soccer ball is curved. In this way, it's called a positive curvature because it's shaped like a ball. And if you have a positive curvature, you can very well cover your space with pentagons. Now, if you take heptagons with 7 corners, you run into the opposite problem. You don't have enough space. You kind of want to stretch space a little to squeeze in this extra bit of tile. And this is precisely what hyperbolic space does. So to get to a connection with this previous formula, if p minus 2 is times q minus 2 is smaller than 4, then you can cover a surface of positive curvature. And there are actually 5 solutions to this, and these are the Platonic solids. If this ratio, on the other hand, is larger than 4, then you can tessel the hyperbolic plane. And now you see, then it just proliferates. There are infinitely many solutions to this equation. So most tessellations you can think of are actually hyperbolic. A very beautiful sequence that I particularly like, but that's my that's my personal bias, is the sequence where the coordination number is 3, like 7 free heptagons, 8 free octagons, 9 free nonagons, because it's kind of a generalization of the hexagonal lattice, which is 6, 3. So we will be quite interested in this talk about the 7 free, just because it's a good representative of hyperbolic lattices in itself. So let's study the properties of this 7 free lattice a little. So I make a lattice out of heptagons. I start with the first heptagon and I count how many lattice sides I have. Well, if I have one of these rings, I have 7 sides. Now I add this second ring and I already have 35 sides. So the sides are on the vertices of this graph. Now let's add another ring. Then I already have 112 sides. Another ring, 350. Another one, 847. So every time I add another layer of heptagons, I add as many sides as I already had. So it completely bunches all the sides on the boundary. And if you were to go, say, into 7 generations, so you roughly have 7 sides, if you go across this diameter, which is called the graph diameter, then you would already have 100,000 sides. So you have an exponential growth of the number of sides with this graph diameter. And for this heptagonal lattice, you can actually show that the total number of sides in ratio to the boundary number of sides is the golden ratio of 1.6. So you can see that most sides are at the boundary. And this gives you also a hint how holographic theories can work, right? If you assume, say, the boundary carries a quark-gluon plasma, there's a lot of boundary sides, so it has enough space to host this whole many-body system. And then the bulk is, if you wish, actually moderately sized compared to this boundary. So that's a very characteristic feature of hyperbolic lattices. And as I already told you, in Circuit QED, Alicia's wonderful experiments, they realized such a lattice using waveguides and superconducting resonators. And it's a very simple Hamiltonian within some approximations. Namely, it's just photons move on this lattice, and their physics is described by this tight binding Hamiltonian where you can just hop from one side to the neighboring side. And if you are a photon moving on this lattice, you would think you live in hyperbolic space. That's a beautiful thing, right? We can only tessellate the hyperbolic plane with heptagons, but if we realize a heptagonal graph, then it is a hyperbolic space we realize. So it goes in both directions. That's a very wonderful idea. And the way you should think about this Hamiltonian is rewriting it in terms of this, what is called the adjacency matrix, which is just a matrix which has an entry 1 if 2 sides are connected by an edge, and 0 if they are not. And then you can just sum over all sides, because most terms in this sum are actually 0. And this object, this matrix, which is just n times n, if you have n lattice sides with 1s and 0s, this is called the adjacency matrix. And it uniquely specifies the graph. And it's a central object of graph theory. And you see, you can basically plug in any graph you can think of by just specifying this adjacency matrix. So it's a wonderful conceptual thing to do. And you also see it doesn't really matter how these sides are arranged for this adjacency matrix. So the topology of this lattice is the only thing that matters, not really where the sides are. So for instance, you might just arrange these sides in rings and then connect these rings with the right links which point outward. And this is what is done in experiments. So these are the experimental things that have been realized. And what we now wanted to do is we want to derive a continuum approximation. So we want to replace this adjacency matrix by the hyperbolic Laplacian, which I will tell you in a second. And we want to replace sums over sides by integrals with the hyperbolic measure. So we want to get rid of this whole lattice. Why do we want to do that? To begin with, it's conceptually important, because we want to know if we can simulate, say, a curved space quantum field theory by just putting photons on this lattice. I told you photons think they live in hyperbolic space, but so to say, is it really the real deal? Is it really what we want to do? Or is it just some sketchy version of a hyperbolic lattice, a hyperbolic space? But then also it's computationally advantageous, especially for large lattices. So I've shown you that as soon as you have, say, 10 generations of layers, then you have 100,000 sites. So you really run into problems just diagonalizing the non-interacting system. So if you have a continuum approximation, you might be able to treat really large systems much better than just direct diagonalization of the discrete system. So how do we do this continuum approximation? Well, we first need a continuum. And there's this very wonderful model of hyperbolic space, which is called the Poincare disk model. And it looks the following. So the Poincare disk model consists of all complex numbers with magnitude smaller than 1. So the interior of the unit circle, and complex numbers will be represented in this talk either on polar coordinates or x plus iy, so just the usual thing. And you should be aware that I set this radius of the disk to unity, which is the only reasonable thing to do, but this is a choice I do, right? I could choose a different capital R as the radius, but then I would have to carry that around. Now, in order to make this a hyperbolic space, I take this set of points and equip it with a metric. So I define a distance notion in this disk, which is the following: 2 points which are infinitely close together have a distance which is the Euclidean distance, but it's divided by 1 minus absolute value of c squared. So if these two sides are close to the boundary, this distance measure blows up. And the result of that is, for instance, that all these points on this lattice have the same hyperbolic distance. So you would think that the sides on the boundary, they are closer together, but this is just our Euclidean projection. In fact, they all have the same distance from each other. And another result you see is that the boundary is infinitely far away from every point of the interior, because you would divide by 0. So each point on the boundary is infinitely far away. It's not contained in the Poincare disk. And for instance, the geodesics are semicircles which intersect the boundary orthogonally. Now, it looks like these points in the middle are kind of, they are closer to the origin than, say, these points closer to the boundary. But I told you this space is infinite. And in fact, there exists a set of isometries, which are the metric preserving mappings, which just goes as follows. So you take any point C out of this Poincare disk, and then you can multiply it with a phase. This is a rotation about the polar angle. But you can also make this transformation, which is called the Möbius transformation, where you pick any side A from the unit disk, and then you take C minus A, 1 minus CA bar. And what this transformation does, it exchanges A with C. So if in the beginning, say, side A was here, after this transformation, A will be in the origin. So this transformation exchanges A with the origin. So any side is equivalent here. So it looks like this would be the origin, but actually each point here is equivalently the origin. It's the same as in Euclidean space, where you can always apply a translation, which brings any point you choose to the origin, and then you have a new origin of this point. This group of transformations called Möbius transformations, described by this group, PSL2R. So this can be represented by 2 times 2 matrices, and since matrices don't commute, this is obviously a non-commutative geometry. And now, equipped with this metric, I want to introduce a differential operator, which looks bizarre, but you will see that it actually makes sense, which is called the Laplace-Beltrami operator. And it's defined the following way. So you take your metric and you introduce this metric tensor, Gij. So in our case, this would just be a unit matrix with this prefactor. And then you define this differential operator delta with a small sub-index G, which tells you it's the metric. 1 over the determinant of G, di, square root of determinant G, Gij, which is the inverse operator, and then djf. So why on earth would anybody consider this operator? Well, the reason is you can define a canonical scalar product on this metric space, which looks the following. If you have two functions f1 and f2, then you just integrate over this space, but you need a volume element which is invariant under these isomorphisms that I've shown you. And this is precisely the square root dat G. Maybe you've seen that in discussions of curved spaces several times already. And then it's actually a one-liner to show that this operator is self-adjoint with respect to this scalar product, because basically this 1 over that g, this kills this that g. And then you have this expression, which is perfectly symmetric in I and j. So this operator is clearly self-adjoint. So the R-quad definition makes a lot of sense in hindsight. And then if you have a metric at hand, you can just compute this operator. Say if you take the Euclidean metric, this operator is just ordinary Laplacian. So that makes sense, right? If you have, for instance, Minkowski metric, this operator is the box operator, where you have this characteristic minus sign between space and time. And for the Poincare disk model, it's also not that bad. So this differential operator, which is uniquely defined by the metric, is just the ordinary Laplacian times 1 minus r squared, right? And it lives in 2 dimensions. So this is what we call the hyperbolic Laplacian. And you would kind of expect that any continuum theory of tight binding, of hopping on this hyperbolic lattice, must give you this Laplace-Beltrami operator. It's the most canonical choice. And in order to do that, you have to embed the graph into the Poincare disk. So I already told you that all of these sides have the same hyperbolic distance. And this distance is actually a fixed number. You cannot choose that to be small. It's very different from Euclidean lattices, where you can make a small lattice constant. Here, the lattice constant is in ratios of this capital R, which I set to 1, is 0.283 for the heptagonal lattice. It's not tiny, but it's also not too bad. So you might think about having a continuum description, which is an expansion in powers of this lattice constant. And we actually did that. So I have to be really brief here. So feel free to ask me afterwards or look into our nice paper. So you have this hopping term in the Hamiltonian, which just tells you if you sum a side over its neighbors, so you evaluate a function at its 3 neighboring points. Say if this side is Ci, then it has 3 neighbors. And this can be expanded in a Taylor series. And the first term is just 3 times this function. Okay, then nothing happens. The linear term vanishes, and the quadratic term is precisely h squared, which is related to this lattice constant, which is not tiny, but small. And then this hyperbolic Laplacian. So you start from a graph, you put it on a Poincare disk, you make a Taylor expansion, and this operator shows up. I think this is really very beautiful. It's very natural how it appears, and it's not any other operator, it's precisely this one. But you have, of course, cubic corrections and quartic, which are smallish, but can sometimes be important. The other thing I wanted to do is replace lattice sums by infinite integrals. That's a little more involved. Let me just tell you, if you sum a function over this graph, you can also just integrate this function with this interesting measure. And this is precisely the invariant measure I've shown you on the previous slide. And you have to restrict your Poincare disk to a finite radius capital L, which is smaller than 1. And the relation of this capital L with the number of sides of the finite graph is this beautiful formula, which is just the square root of n over n plus 28. And I've shown you that this n grows exponentially with the graph diameter. So this is a number which is very close to 1. So here, this number of rings, if you have 1 to 10 rings, this effective disk radius, capital L, quickly goes to unity very closely, but never quite approaches it. So even if you have an infinite lattice, you wouldn't really reach the boundary. So you have this beautiful mapping, and let me be brief in this last application. So let's assume you had something like a Bose-Hubbard model, right, on this lattice. Then you have this hopping term, you have chemical potential, and you have a Hubbard U. And then the continuum, and you have canonical commutation relation. In the continuum version, you would just replace the sum with this hyperbolic volume element, this hopping term by the hyperbolic Laplacian, but all the local terms remain untouched. So that's a very beautiful implementation of interactions in hyperbolic space, because you don't have to fine-tune that. It works by itself. And the commutation relations are those of curved space. And as an application, you can compute, for instance, correlation functions, the expectation value of AI, A dagger J, which of course experimentally a very relevant question. You can approximate them just by the continuum Green function. It's actually the Green function of this hyperbolic Helmholtz operator. So the reason we call that the Green function is because it is the Green function of a differential operator. This can be computed by the method of images. And this is just a comparison for two different frequencies where we plot the graph green function and this match with the continuum. And you see they fit perfectly already for a rather small lattice with only 112 sites. You can show that you get some emergent conformal symmetry, since the continuum green function for very big systems only depends on the hyperbolic distance. The same must be true for the graph. And we verified that this is actually the case. So we have an emergent conformal symmetry on the graph. This correlation function is a function of only the hyperbolic distance of the two lattice sites for big enough lattices. And with that, I want to thank you for your attention.
Great. So we started a little bit late, so maybe we'll sort of give like, let's say 5 minutes for questions. So questions for Igor, I guess you can just go ahead and ask. Any questions? No. I'm sort of on this paper, so I'm not gonna ask.
You were too clear, Igor.
That's okay.
Well, I can wait for a few more seconds, and then maybe.
So yeah, I have a question. This is
Perfect.
Colin Rowlands here. So your book had like some isometries that were conformal symmetries. Does that mean that if you go to the boundary, there should be some conformal field theory description of it?
That's a very interesting question, because it is a discrete system after all, right? If you look at these lattices, the boundary, if you have a finite system, let's look, say, at this plot, right? The boundary is still finite, and there's a paper which says that the boundary of this is actually a 1D quasi-crystal, and that there exists a certain quasi-crystallish conformal field theory on this boundary. So it's very interesting. It's a very good question. It's a very interesting research topic, what the CFT version of this boundary is. But since it is a discrete system, it has some discrete effects. So, but if you had a continuous hyperbolic space, the boundary would indeed host this CFT. That's a very good question.
More questions for you?
This is Charles Clark. This is Charles Clark here. So looking at this figure we see on the screen now, it's as if you have a construction that's based on a Platonic figure. Then was it hexagon? Are there other geometries like a triangle or square or other n-gons to which you could generalize this, or is it based primarily on the sixfold similarity?
No, it's an excellent question. So any PQ you can think of which has this ratio larger than 4 qualifies. So for instance, what I could do is I could take 3,7. Then I would have triangles, and on each vertex I have a coordination number 7. This is actually the dual lattice of this, where you have a point in each face. So one way to construct new lattices is to go to the dual lattice. Like the triangular lattice is the dual lattice of the hexagonal lattice. The same I could do here. But I could also take 5,5 or 120, 1,400, 1,000. So all of these tessellations which have a P and Q, where this product is larger than 4, would be a valid hyperbolic tessellation. I mean, they get a little insane at some point, but in principle, you could do all of that. It's just important that this ratio is larger than 4, and this only excludes 8 cases, in fact.
Is there a possible extension of these ideas to something like the Penrose aperiodic tiling of the plane?
At this point, I don't quite know, because these tessellations only use one polygon. So we would call this is a homogeneous space. Each point looks the same. And these transformations I've shown you, each point is equivalently the origin. If you have a more complicated tessellation, then you have some fine structure in this. And then if you think about maybe some more interesting unit cells, you would still have a periodicity of that. But our framework applies to these PQ lattices for now.